Hi everyone and welcome back to your channel Fundamentals of Engineering with Farhad Fluid Mechanics. In this example, we review a very interesting problem in a horizontal bend which the flow rate comes into our system and we want to calculate the discharge and also the vertical component of the resultant force which keeps to hold the bend in place. So in this example, we have like water flows through a horizontal bend and discharges into the atmosphere. When the pressure gauge is reading 10 psi, when you can easily see this is like in psi pound square inches, and the gauge just shows the 10 psi. And we do know the resultant force in x direction is provided to F sub AX is equal to 1440 pounds, and we want to calculate first the flow rate which moves through the bend and also the vertical component of the resultant force which required to hold the bend in place. Ignore the friction. So first of all, we need to jot down the momentum equation in x direction. Summation of F sub x goes zero. My bad. Summation of forces in x direction is equal to rho q delta v, density of water times the discharge times the difference in the velocity comes to the bend and velocity goes out from the bend. So if we jot down the equation, first of all, V1 for velocity in the cross section one is discharge over the area. And likewise V2, the velocity which water leaves the bend, is V sub 2, that's also discharge over the area to which both of them are provided in feet squared. So the forces which applies to the bend at the very beginning cross section, that's P1 A1. And then if we just consider this is a positive x direction, like the positive x-axis just goes by positive x, then P1 A1, the pressure applies at the beginning of the cross section minus the, because it just shows 10 psi there, and then F sub AX is 1440 pounds, and that's equal to rho q times the velocity which leaves the bend at the horizontal direction is V2 cosine of 45 degrees, and because that's opposing our positive direction, that's a negative V2, and then subtract it from V1, which is this one. V1 comes to the system, and if you jot down the equation, then replace V1 and V2 by these two formula, simplify the equation, it just gives you P1 A1 minus F sub x is equal to rho q in brackets negative instead of V2 q over 2 times cosine of 45 degrees minus V1, which is q over A1, and then multiply q in both part, that's rho q squared over A2 cosine of 45 minus rho q squared over A1. So far we have this equation, and the first part of the problem we are looking for the discharge, and the only unknown in this equation is discharge. So if we rearrange the equation, every part is provided. We have like the parametric formula for discharge, which is q is equal to a square root of blah blah blah. Then if you look at the pressure gauge, which shows 10 psi, and because everything is in feet squared, and then we need to convert 10 pound square inches to pound per feet cubed, a pound per feet square, and this is like 10 psi is equal to 0.069 pounds per feet squared. Then the pressure gauge reads 10 psi. Then replace the numeric value. We will read like our P1 A1 is just comes here. This is our pressure. This is area 1, which is here, 0.2 feet squared. plus Fx, which is like 1,440 pounds over rho, and rho density of water is equal to gamma over g. Gamma is 62.4, g in USC's customary unit is 32.2, and then the rest of the equation. Mhm. And this is A2, this is A1, which are both provided. So if you do the math, it just gives you a discharge of almost 7 feet cubed over seconds per seconds. So that's the first part of our problem, and the second part of our problem was is a calculation of f sub a. By intuition, we can easily see if the water comes through this horizontal bend and shoots down through the uh, this part of our bend, you can easily think of the force needs to keep the bend in place should be upward. So this is by just intuition, this is not the correct direction. So just flip-flop the arrow, summation of forces in y direction is equal to rho q delta v, but this time in vertical direction. And if you jot down the equation for that part, that's F a sub y, because that's the only force applies, and then density times discharge, and the only velocity in y direction is v sine of 45, and that's a v2 sine 45. We have our q, and Fay is equal to rho a v squared. If we just replace q by av, then sine of 45 degrees. So again, rho comes from gamma over g times area, which is zero point 0.1 a2, and v2 is just a comes from the division of area. So if this is our V2, we can easily calculate F is equal to F a sub y, the vertical component of resultant force is rho a V2 squared sine of 45. We already have the Q, but V2 is Q over the area 2. So we can just jot down that, and it just gives us a V2 is equal to 70.1 feet per second. Then F a sub y is equal to a 673.36 pounds. And then for our problem, we were looking for the discharge and also vertical component of our force to keep it on place. Thank you. We'll solve more problems.